There we go. Okay.
So now's your chance to iron out any problems on chapter 1 and 2 for exam 1. I always open the floor first, because once I get started talking, I might not hit the topics that you need. We'll cover the ones that are giving you trouble first. Okay? If you don't say anything, then it's my cue to start talking.
So we're needing to know scientific notation, right?
Oh, definitely.
And the difference between scientific and exponential.
Exponential? Uh-huh. Right, exponential is the general case. Let's see. Do it this way. Something like that. Exponential could be any size of the coefficient. So we could say 34 times a third. That would be exponential. Scientific is a special case. This has to be between 1 and 10. Okay. That's scientific notation.
And if you only put the what are they called? Significant figures in scientific notation.
It works either way, right? But this is a good way to find out what they are.
Okay.
Right? Because if you had this one's simple, because they're all non-zeros. But if there's a decimal, and say we got a 0 here, you can still keep that 0. It is significant. Or if we had a 0 in here between two non-zeros, that would be significant. Get a 0 out on this end, and it wouldn't, for large numbers, that wouldn't apply. But for very small numbers, let me be consistent. 3, 4, 7, 9. 0. Yeah, something like that. Throw those out. They're not significant.
So how would you write that in scientific notation?
Right, 3.479, keep it 0 to the right with a decimal. Same rule. Those are thrown out, but we move 1, 2, 3, 4. 10 to the minus 4.
So it's a good way to figure out what is significant and what's not.
Mm-hmm.
Okay.
Yep. Because now all you have to do is count the digits in the coefficient. And you got 5 significant figures there. Okay. Were there any specific problems in the review document that you want to discuss? Those are general terms that we discussed earlier. Let's see. You know how to tell the difference between accuracy and precision. Right. You remember our bullseye?
Accuracy is group. Wait, accuracy is towards the middle and precision is group.
Right. This would be the true value or the accepted value, one or the other. And if the average of your values is right there, then you have accuracy. Right. So one possibility is you have a value there. That's accurate. But they're grouped very tight. So they're also precise. So this is accuracy and precision. Good. Accuracy based upon where the average value is, right in the center, and precision based on the grouping, very close. Your various samples are close together. If we had another one, say, here's your bullseye. Say we had that technically is good accuracy, because the average of those four is right here. But for precision, because they're spread way apart. Another possibility is that. So that would be more accuracy. Because the average of those is up here, nowhere near the bullseye. But they're good precision because they're grouped tightly. Okay, and then the last one. Something like that. Both of them are poor. Poor accuracy, poor precision.
You really have to try and get that one. And you really have to try and get that one.
Yeah. Those are the four possibilities. Yeah.
Like, getting the poor accuracy and poor precision is very hard to do unless you're trying.
Now, what's the ideal for a hunter cycloscope? That one. But what's most often possible probability if you had your rifle sitting up since last season? Usually this one. You get a good grouping, but it's way off. So you just adjust your scope, bring the whole grouping down. Try it again to be sure. Get that one.
The easiest to hope for is poor accuracy.
Good precision.
Yeah.
It's easy to correct that one.
Good accuracy and poor precision means that their instruments are not correct.
Mm-hmm. Sometimes you'll see precision referred to as reproducibility. Oh, that's going to happen if I don't do this. Pin the video. There we go. That keeps the others from jumping into my main screen. Okay. Let's see what else we can come up with. How about number 16? We didn't actually talk about this one in class. Not directly. The amount of uncertainty in a measured quantity is determined by what? Well, it looks like there are mixtures of potential here. We start from the bottom, the skill of the observer only. And then move up to C, limitations of measuring instrument only.
Well,
actually, it's both.
Yeah, it's a bit of both because the people get things wrong all the time, and it's called the human error.
Yep.
Which needs to be accounted for because if you don't put that for human error, your calculations are not right.
Right.
And then measurements can always be precise because of limitations of
Observer and the instrument.
because basically we can't measure something as small as an atom without having something as small as an atom.
There's you can also interpret an observation in two other ways. Not an observation, I say multiple observations. Can either be, the error can be classified as either systematic or random. We generally take care of random errors with statistical analysis because statistics is based upon randomness. The systematic error says that there's either some repeatable mistake that the instrument is making or a repeatable mistake that the observer is making. And those are more difficult to correct and sometimes identify.
Because an observer can be biased.
Usually are, yeah. And then your instrument, a lot of instruments now are like black boxes. You really don't know what's going on inside. The worst offender is NIR, an analytical instrument. It means near infrared. It takes an infrared spectrum of your sample, usually a reflectance sample. And then you take several standard samples and put them through the procedure. And then the electronics on the inside creates an algorithm for that type of sample and those concentration ranges. And it doesn't tell you how it does it. So you put your sample in and it spits out a number. You just have to believe it. So I never did trust NIR analysis very much. There might have been some theory involved, but it wasn't disclosed to me.
When knowledge that's shared becomes obsolete very quickly.
Yeah. And my guess is that the reason that it wasn't shared was because the instrumentation was proprietary. So the developer didn't want to share it because they didn't want somebody stealing their business.
Put a patent on it.
Yeah. They probably rushed it to market and it was patent pending. And that happens a lot. Okay. Let's see what else we can find. That's useful exercise. How about number 32? When you're combining calculations, or maybe you want to do something simpler. How about 27 first? Let's do 27. No, multiplication and division, if that's all there is, then you have a number that's, for this example, no, that's not. Let's try it. I'll just make one up. Multiplication and division just says if you have a number like this times divided by you have something like that, multiplication and division only, how many significant figures can you keep out here? There's 4 here, there's 5 here, there's 3 here. So this one can only have 3 significant figures. Right? If it's only multiplication division, then your answer can only have the number of significant figures in your least number here. Okay. I don't know what that would be. Now we can do it. Let's complete the loop. About 1.23, 4.3, 5, 7, 9, 3.34. Oops. Something's wrong. Right. Somehow my format got changed. Display. Scientific. Okay, now I'm gonna try again. 1.23, 4.35, 2.84 divided into that. And my calculator spit out this stuff. Okay? So if you've only got multiply and divide in your calculations, keep everything your calculator gives you. Don't round off, say don't do this one and round it and then divide that out. Just keep them all. Then go back and say, we can only keep 3. So we've got to round to those 3. This one's less than 5, right? So we get to keep that as our answer.
Is there any percentage problems?
Percentage. Well, if you round each step, yeah, you're going to be way off.
Because there was an easy thing to figure out.
What, if this were percent?
Just if there's not even about this question, just percent in general. Like 25% of 10 is 10% of 25.
Oh, yeah. Yeah.
And one is much easier than the other.
They're interchangeable, yeah.
So it's like, that's an easy way of figuring out.
You want to do the calculation in your head? Yeah.
It's, one is much easier than the other.
So what if we have combined expressions? Well, let's do one that's not combined, 27. Go back to 27. And this one says, calculate the following answer to the correct number of significant figures. So we have 4.0021, and then we're subtract 0.179. So what you do when you're going to add or subtract is you line up the decimals. Like that. Then you subtract, and it's understood to be 0, but there's not a 0 there. 1, 3, 7, 2, 8. I think that's right. Yeah. Okay. Now you have to decide how many decimals you can keep, and you have to go to the least one right here. Like so. That's less than 5. That's your answer.
Like, why would that be 8 and not 9?
Here?
Yeah.
Because they're subtracting 1 from 9.
No. Are you?
Yeah. 9 from 12 is 3. 7 from 9 is 2. 1 from 9 is 8. 3.
But why would you change the 0 to a 9 at the same 0?
Okay. 9 from
12 because
because it's like
and then the next one over is just a 9. And
9
that's
because
2.
you carried 1. 7 from 9 is 2.
But that understand.
What can you take 1 from 0? Excuse me. You're right. You're right. Yeah. So 7 from 9. So this became 9 because we took 1 from it.
Yeah.
Right, so from 1 to 9 is 8. So it's still the same answer.
Wait. No, that became 9 because you took 1 from it from the other side, but you don't change the 1 in front of it, do you?
He's right. The instructor's right.
See? Okay. So if we're going to subtract something from this one. All right. So what we've done is we brought that one down. We have to take 9 from 12.
Yes.
So this one becomes
9.
9. But where did that one get the 9? It used to be 10. Where did that 1 come from? It came from this one.
Okay.
Where did that 10 come from? It came from this one. Sort of a cascade
Okay.
effect. Okay, so that's our answer for subtraction. If you have an explicit decimal point. So that would be the answer for 27. But the example I gave you in class was one in which we don't have an explicit decimal point. Right? So you have, let's take these numbers and convert them into something useful. 4, 0, 0, 2, 1, and 1,790. Now we're going to subtract. How do you line up the decimal points there? And how do you know? If you've got that 0 here, do you get to keep all of them? No, you can't, because that 0 is not significant. It would be if we put a decimal there, right? But we don't have a decimal. So that means we have to round to that position. And that makes it, let's see, 3, 2, 3, 1. 1. Then we have to take the round to this position because that one's not significant. So we're limited to there. So we have to round to that. There's no decimal. Okay. The authors don't tell you that. I don't think they tell you that in the book. They just assume that there's a decimal point there that you line up. It's easier to explain it that way. But if you're in a situation where you're subtracting two numbers and there's no decimal point explicitly given, then you look for trailing zeros. And the trailing zero is not significant, so you have to move over here.
So why do you leave the 0 in the answer?
Say again?
Why do you leave the 0 in the answer? If you're rounding the 1, could you leave the 0 off?
No, you leave the 0 because it's a placeholder.
Okay.
Yeah, if you don't have that 0 there, then it shifts the whole number by tens the wrong direction.
Okay.
But you don't put the decimal in. You leave the decimal out. That means that that trailing 0 is not significant.
Okay.
But wouldn't the answer only be 3 significant numbers? If the least was 3 significant numbers, would the answer be 3 significant numbers?
Because you can't count the 0. Exactly.
You have to put it there, but you don't count it.
Right, you don't count it as significant.
Can you do another example?
Yeah, let's see. Let's see, I already used that one. Let's see if I find another one. Either that or I have to make one up. Okay, let's make one up. Suppose we have,
in case we're wrong.
and then we want to add. And then we want to add like that. We're going to add those three numbers together. Okay. So you just line up the understood decimal, which would be here. Get your ones, tens, hundreds, thousands. So we add them together. 3, 12, 6, 9. See if I did that right.
Yes.
12, 6, yeah. Okay, now you have to decide where your rounding point is. You look here, that's significant, which we put it there, but these two are not significant. So you'd have to round to this position. Now, and put these two placeholders in there for those two positions. If we didn't do that, we left them off, then our answer would be 962, not 96,200. But as it is, that's the correct answer with the last two zeros being non-significant. Okay,
I have another question.
okay.
On, problems 18 and 19.
Okay.
How do you know that it's -4 and then 19 is +5? How do you know if it's a negative or positive?
It's the direction that you move the decimal place when you make the conversion.
Okay.
18. Okay, so our standard notation is this, 3.
Okay, he did move it that way.
And we're going to move the decimal 1, 2, 3, 4 to the right. So that makes our coefficient that. And then we move 4 to the right means negative.
Okay. So every time you go right, it's a negative, and left is positive.
Right. If you're going from standard notation to scientific, move to the right, it's negative. And that makes sense, because this is a really small number, so that's got to be negative. 19. Okay, so 19, we've got 165,000 with no decimal place. I mean, no explicit decimal. So we're gonna, that's our anchor point though, let's say that's our anchor decimal, but not explicit decimal. So 1, 2, 3, 4, 5. 1.65 times 10 to the 10th because we moved to the left.
Yeah.
And we have to leave these zeros out because they're not significant.
Okay. I'm sorry, I thought it was a period after the 5 instead of a comma. Or, I'm sorry, I thought it was a decimal instead of a comma. That's what confused me.
Oh, yeah. Yeah, that's a comma.
Okay.
Well, that makes a lot of sense.
If this were Europe or any other place in the world, it would be a decimal.
Is comma,
Because they use
because decimals aren't a thing
decimals aren't a thing.
in writing in European.
They don't use periods ever.
They use periods, but they only use them as periods, they don't use them as decimals.
Oh, they're trying to distinguish between periods and decimals.
Yes,
Right. Periods at the end of a sentence versus decimals in a number.
yes,
So they separate those by making it a comma instead of a decimal.
and not exactly just a comma, they make it a special comma. That's not the comma that you put in
Oh, it looks different.
thousands, yeah.
Yeah, okay. I'll take your word for it.
It's like a dot with a, instead of a,
Is that a straight tail?
it's a dot comma. Rather than,
Oh, rather than this, it's kind of like that?
yes,
Okay. Okay, now, how about where you have combined? Let's see, here we go. Number 32. If you have a combined operation like this one, 3.478 times 1.164 divided by 2. I'm leaving out the units of measure because we're focusing on the significant figures. Minus 0.169. Okay. So how do you do that? There are no parentheses in there to tell you how to do the calculation. So you have to go back to the order of operation. Right? Parentheses, exponents, multiply, divide, add, subtract. So multiply, divide comes before add, subtract. That means you do this one first. And in that case, you will have to round. You have to round this group, then combine it with this one. Okay, so let's just do that one real quick. let's do this one. So 3.478, and then times 1.164, and then divided by 2. So this part here is 2.0242 out of my calculator. Then you take the least number. That one's 4, that one's 4, this one's 3. So we're going to round to that position, 2.02. Okay. Now, you take this one, line up the decimals, 169, and subtract that from 202, and I get 1.85. Well, those are not lined up really well. 0.1.
Oh,
There we go. That's better. Let me do this with my hand. 1, 6, 11, 5, 1, 9, 8, 1.85. Then you go to, you're limited to that one. So we round, that's 1. So it's 1.850. Oops, my mistake. What's the mistake here? I can't, right?
Yes.
Yeah. And if there's a decimal or the 0 to the right, that we're saying that 0 is significant.
oh, wait, I added.
It's not significant. Right, so it has to go. Right? Okay. Sure, that's the one. Yeah, okay. It agrees with my key.
I do not agree with the key.
Yeah.
I do not agree with the key.
What's,
I do not agree with your key.
because I looked.
No, I said I'm not agreeing with the key.
Oh, you're not agreeing with the key.
Yes,
Why?
What's wrong with it?
I just don't agree with it.
Oh. A contrarian, are you?
I like to do some of those.
Okay, let's see. Does anybody have anything else to do with that? How about dimensional analysis, unit conversions?
If you multiply units, you can stick them together.
Keep track of your units, yes.
Because if you have 10 miles an hour, which is times, if you have 10 miles per, which is times 1 hour, it's 10 miles per hour,
Okay.
right?
10 miles divided by hours. Yeah.
Yes, and so you can keep, if you're multiplying or dividing by 2 different measurements, you keep it, right?
I'm not sure I understand your question.
Okay, so say for example,
Yeah, give me an example.
you have moles times volume.
Okay.
That would be moles per volume, right?
No. That would be, well, what are your units of volume? Say liters?
Yeah.
Okay, that would be moles.
Moles per liter.
That would be your units multiplied.
So if you're having, that's what I'm saying, if you're having 2 different measurements like moles and liters, if you multiply them or divide them,
It's a different composite. If you divide them, it'll be moles. Right? You know? But if you have an operation where moles is in the numerator and liters is in the numerator, then it's just moles, liters.
okay.
Yeah.
So you can, but you keep the 2 separate.
Yes, Yes, there's no cancellation there. Right.
Okay.
Right. They stay together in the answer.
If you're not converting, they stay together.
Mm-hmm.
Okay.
Yeah. I see what you're saying.
That was a question that I was having, because like we were doing conversion factors and every single conversion had one unit and then another unit. And I was just thinking, wait, what if there's two different units that are in the same question?
Right. If you have a, let's see, if we have some value and you have its units of measure are joules, seconds, or mole, and you need to convert it to something else, you look to see where you're headed. And if you're going to have seconds in the numerator down there, leave them alone. If you're going to have joules down there, leave it alone. If you're going to change moles to something else, that's the one you focus on. If you're going to change all three of them, and do them one at a time. So you'll have a conversion factor in here for joules and something else. And then you have one in here for moles and something else. Moles will cancel. And then you'll have one in here for seconds and something else. And the seconds will cancel. You do each one independently. Yes. That's the only way to keep from messing up.
I just wanted to make it clear just in case something popped up.
Mm-hmm.
I didn't know.
How about 46? Here's a dimensional analysis. During a physics experiment, an electron is accelerated to 93% of the speed of light. What's the speed of the electron in miles per hour? Okay. So we're given that the electron is traveling, let's see, a little, physics, they say U instead of V, just to keep confusing it with volume. So the velocity of the electron is equal to 93% speed of light.
Which is the constant.
Yes, in a vacuum is a constant. It travels through something else besides a vacuum, it's changes, which is the whole premise behind refraction. And the question is, what's the speed in miles? Okay, so we can't use, that's a dimensionless number. Parts per 100 means nothing. So we have to find out what the true value is for this one. That means we multiply the fractional equivalent of 93%, which is 0.93. Does anybody in? 0.93 times the speed of light, which, yeah, we're going to take this, round it off to meters per second.
That is a stupid amount of speed that we have never gotten up to.
No, and theoretically you'll never get there. For another reason.
What about faster than light travel?
Oh.
And postulated. Okay, well there's the actual speed of the electron. So to make a long story short, what happens is, as your speed increases, your inertia increases. It's interpreted as mass. And when you get to the speed of light, your mass is infinity. So there's not enough energy in the world to make it go faster. As long as you're in this, I'm going to use the right terms. Your space-time continuum. As long as you're in this. The only way you can go faster than the speed of light, apparent speed increase, is to warp space.
Break the space-time continuum.
So you spread the space out ahead of you and you contract it. No, you contract it in front of you and spread it out behind you. right? You change the medium through which you travel. That's the idea,
That is weird.
theoretically speaking.
That is weird.
Okay, so we've got meters per second. So we're on our way to miles per hour. All right. So since we've got two units of measure, both of them are going to change. Let's do one of them at a time. Okay. So let's see. Let me look at the problem, see what values were given. Conversion factors were given. We're given speed of light, and kilometers changed to miles. So if we know kilometers and miles, we need to change meters to kilometers so we can use that conversion factor. So how many meters in a kilometer? Into the third. That takes care of meters. Now we can use that conversion factor that was given to us in the problem. Miles on top, kilometers on the bottom. Why? Because we want kilometers to cancel. So 1 kilometer is 0.6214 miles. Okay. Now we've got miles. Now we want to change seconds to hours. So if you know what the conversion is, fine. If you don't, then do what you know. Right? So the seconds is on the bottom. So we put 60 seconds on the top is equal to 1 minute. And then we convert minutes to hours. Okay? So now we have miles and hours left over. And the rest is just crunching numbers. That's dimensional analysis. Our pathway was dictated by the dimensions. So we take this number, divide by 1,000, and times 6214, 0.6214, and then times 60, times 60 is 3,600. So it should be 6.24 times 10⁸ miles per hour. And I kept 3 significant figures from here, 3 here. And what do we do with the conversion factors? They don't count. They're exact numbers.
There's 0.
They have an infinite number of significant figures. Right. Question? Okay. Or was that a math?
That's still really, really fast.
Oh, yeah.
Like,
Let's see. What is it? We learned before metric system, and I think in grade school, metric wasn't really pushed a lot.
Can you maybe go over another one like that?
We learned 186,000 miles per second was the speed of light. So if you divide that by 60, it should come out something. No, if you divide that by
60 minutes.
no, divide it by 3,600. Right? Because we changed seconds to hours. We just want to keep it seconds, so we don't need to change seconds at all.
Yep.
And that should give you 186,000 miles a second.
It's stupidly quick.
Okay, let's see. Our Zoomers want us to look at it like that. Okay, let's see if we can find it. You mean the one that's a complex conversion?
Yes.
Okay, let's see here. Oh, the one right below it. Looks like a good candidate. Yeah. So, you're planning a road trip, a spring break, and the distance is 2105 miles. If your car gets 33 miles per gallon, miles miles per gallon. I don't know what that value would be. Let's see. That would work. Just make something up. And gas costs $3.199 per gallon. All right. How much will it cost to get to your destination? So the question says, just how much would it cost to get from here to there? It doesn't assume that you're coming back. Maybe you like it there and want to stay. So it's just a one-way trip. So if we start with, we got to go this far. That many miles. We want to end up with the cost. Right? How much money? So how would we convert? We've got these two conversion factors, and we want to have in dollars. This will put us at dollars. Right? So if we incorporate this in there, we got to get rid of gallons somehow. So this is kind of the intermediary. Right? Okay. So that cancels miles and gallons and leaves you with dollars. Let's see what that turns out to be. And then we have 4 significant figures here. Those are conversion factors, so they don't count. So we have 1, 2, 3, 4. All right, that's a 5, so we got 204.1 dollars. And of course, you never write that for money. You got to fill it in the last place. So you need to take $204.10. What if you want to get back? Double it. What if you want to run around while you're down there? Yeah. I was going to say pad it, but triple it sounds funnier. Let's see how much time we got left. I don't want to run out of time and not cover all our topics. We've got about 25 minutes. Okay, let's see. Temperature conversions, right? You just need, of course, if you look at the useful information, there should be the formula for converting. Yeah, right. So that's in your useful information, and that will be on your test. So if you want to go to Fahrenheit from centigrade, I always memorize it this way. But this is also equal to 1.8. So if you know that formula for Fahrenheit, centigrade, or Celsius, then you can rearrange it to find out if you know Fahrenheit, you can find centigrade. So you just put F in there. So say F times 32. Then
You said you weren't working that out.
times equals centigrade. Rearrange your formula. And then, what other temperature do we have? Okay. That's always Celsius plus 273.
0.3.
And actually it's 0.15.
The 0.15 is because,
Well, 273 is good enough for us. It's theoretical anyway.
I don't actually know.
Yeah, you'll never get to absolute zero.
We've gotten close.
Really close. The closest we've gotten with a bulk substance is liquid helium, I think. Liquid helium is very close to absolute zero. And they've done it with some other things too.
Liquid helium.
I think it's about 4K.
The only way to get solid helium is to get it to absolute zero.
Possibly. Yeah. Right.
Yeah.
Let's see, what else? We mentioned density, right?
Oh, wait.
Everybody knows what density means. When you calculate density,
How much of something is in the thing?
right, what is the mass of a specific volume? So for that substance, you need to know what its volume is and then what that volume represents in terms of mass. Then you can calculate density. And it's like any other formula, right? These variables, if you know two of them, you can calculate the third. So if you know this one and this one, you know how much mass. If you know this one and this one, you know what volume it represents. If you're going to measure volume of an irregular substance, how do you get that? Mass is easy, you just stick it on a balance. How about the volume? Right, if it's not a regular object, you can't use a geometric formula to calculate. So what do? The easiest way is by difference. Right? You have a graduated cylinder with a volume up here, and you submerge your irregular object in it, and the volume comes up to here. So that difference is your volume. Okay? That's assuming this is not soluble in water. If it is, you've got trouble. You may have to pick a different liquid, right? If you had a chunk of rock salt, you wouldn't put it in water. You might put it in mineral oil, right? It won't dissolve in mineral oil. Do the same thing. Okay, so that's density. Let's see. What about, now we're getting into chapter 2. What about the laws that we learned? And I think the first one was Lavoisier's. The law of conservation of mass. Right. So, chemical reaction, the mass of the reactants is equal to the mass of the products. You don't create mass, you don't destroy mass in the process. Right. At least as far as we can measure it in our labs. Then you have the law of definite proportion. Let's see, this was Lavoisier. This was Proust. The law of definite proportions is no matter where your compound comes from, however you got it, by purification, by chemical reaction, doesn't matter. The mass ratios of the elements in that compound are always the same. Doesn't matter the source. like you purify water, right? You get that compound, hydrogen, oxygen, certain mass ratio. Or you react hydrogen and oxygen in a rocket engine, and it produces water. It's got the same mass ratios of the elements, either one. The source doesn't matter. Then there's a law of multiple proportions. And this was Dalton, I believe. He said that in any series of compounds that have two elements in them, if you hold one of the elements constant for mass, then the second elements from one to the next to the next to the next vary by whole number multiples. And he didn't know this at the time, but that nitrogen monoxide, nitrogen dioxide, nitrogen trioxide. Holding nitrogen constant, each of these masses of oxygen increases. If this is 1, then this is double that one, and this is triple that one. That's multiple proportions. It's basically an observation. But Dalton did come up with a good one after that. Dalton's atomic theory. Okay? What's the first premise of Dalton's atomic theory?
The atom.
Right. All matter is composed of atoms. The smallest unit. Retaining the element properties. Okay. Then he said something else about atoms. Each element is composed of different atoms.
Just say,
Right, they differ between elements, or among elements, they're different. But within the collection of one pure element, all the atoms are the same. So what he's saying is that the differences that you see between this element and that element is due entirely to the makeup of the atoms in that element. Okay, let's see. Then he said something about chemical reactions. In a chemical reaction, elements are preserved and they're only rearranged. So that supports Lavoisier's law of conservation of mass. Right? If you're not doing anything that changes the atoms of an element, except rearranging them, then the product that comes out has the same number of atoms as went in. That means it has the same mass. Let's see. What am I leaving out? Each element composed of different atoms. Yeah, I guess there's maybe a second statement right in here, or maybe attached to this one we said. Atoms never change.
Untrue.
Right, because they do, we know they do. They change based on nuclear physics, not chemistry. Um, oh,
Isotopes change.
this will be 3. And then 4 would be all atoms of an element are identical.
Isotopes.
That's not true anymore either, because of isotopes.
We can have non-radioactive isotopes, those
Oh,
things.
yeah.
And, they change in a given compound on a reaction.
Non-radioactives?
Yeah, non-radioactive isotopes can be formed in a chemical reaction.
Oh, yeah. I mean, chemistry's the same, but the atoms are not identical. Right, they behave the same. Yeah, there's some argument there too. But for our purposes, all the atoms of an element are not identical because of isotopes. So what's an isotope? Same number of protons?
Same. Different
Right.
neutrons.
Right, different number of neutrons.
Extra mass does change the way it acts,
Yes, it does.
and
But we're not going to labor that point in this class. Enough to remember as it is. Okay. So that's Dalton's atomic theory. Let's see. This is 5.
he was correct about a lot of it.
Oh, yeah. Yeah. He got closer than the ancient Greeks did. He started in the same place they did with atoms. And he refined a bit. Based on evidence. Okay. Okay, so if you have an element, let's say $19. Oh, and this is 19 chapter 2. If you have a mixture of bromine 79 and bromine 79 and bromine 81, these are isotopes, right? They're both bromine. Then, oh, this question has to do with this one right here. So how many protons, neutrons, and electrons are in that? Write the symbol. Right. Protons, where do the protons go? Right, we have 4 positions here that are reserved for information. Right. This one is atomic number. This one is mass number. This one is charge. And this one is numbers of each. So what's the atomic number of our protons, right? So we just need to go to our periodic table. Oops, log in. 35. 35 is the number of protons. How about the number of neutrons? If it's 79, mass number, and the neutrons is equal to 79 minus 35. Because this number is the total of protons plus neutrons. So if you subtract the protons, you're left with neutrons, right? So this is 44 neutrons. And if you're not told it's an ion, assume it's neutral. Which means, how many electrons are there? 35. 35 electrons. Same number of protons because in a neutral atom, pluses have to balance minuses. So what if bromine were charged in an ionic compound, for instance?
It would have to be -1.
-1, because it's a halogen. In ionic compounds, they're always -1. So if we have this one, then we would have 35 here, 79 there. How many electrons? 36. 36 electrons because it's the balance of plus and minus. You have an extra electron, which makes it minus. Why can't we change the number of protons if it's just a balance of plus and minus? Why don't we just say, okay, instead of, let's keep the number of electrons at 35 and say we're going to use 34 protons. It's still -1, right?
That's a different element.
Right. 34 would make it selenium. Then we don't have bromine anymore. Right? So you can't mess with the protons when you're doing these charge balances.
You can ionically charge any element.
Oh yeah. Oh, yeah.
Just
I
send a
mean,
charge.
even the noble gases,
You just have to send a charge to it the right way.
takes a lot of energy because they don't want it. They don't want another electron. They don't want to give one up. They don't want to take one. But,
You can force them.
oh yeah.
Those issues.
Sometimes causes compounds that you would not normally expect.
That would never exist in nature.
Right. Okay, how about we're about to run out of time. How about, naming compounds. What's the name of this one? What do you do first? You look at what are the cation anion. Cation is a metal that comes from transition metals. That means it could possibly have more than one charge. So which type does that make? Type 2. The type 1s have fixed charge for the cation. Type 2 is multiple possible charges. Also in this one, we got a special case. That's a polyatomic ion. Right? So you look up in your list of polyatomics, it should be, it's right there in useful information. It'll show up on the exam. 2- charge. There's only one of them. Remember, the polyatomics act like single units. So that charge is assigned to this whole unit. So those 2 minuses have to be balanced by 2 pluses. Okay? Because it's a neutral compound. So now all you have to say is iron. What's its charge? 2. Sulfate. And that's the name. Let's go the other direction. Suppose we have, let's see, how about this one? We're given the name aluminum oxide. Okay. We have aluminum, we have oxygen in there. Where does the cation come from? Here. Fixed charge. Right? +1, +2, +3. Fixed charge means type 1. Right? So now all we have to do is say, what's the charge on oxygen? In ionic compounds, these are -2. -1, -2. So that means that one has to be balanced by this fixed charge of 3 plus, right? You can't change those. So that means you have to have the balanced charges, and this one's odd, this one's even. The best way to resolve that is cross them. Put the 2 over here, and 3 over there. And just check yourself. 3 times 2 minus is 6 minus, 2 times 3 plus is 6 plus, and balance. And let's see. How about this one? Dichlorine and oxide. What kind is that?
2 chlorine, 8 oxide, 6 oxide.
Chlorine and oxygen come from the same area of the chart.
Wait.
Non-metals.
Is Hep 7?
Yeah.
Okay.
So that makes these type 3. If we're type 3, all you have to do is get your symbol right, chlorine, oxygen, and then write in how many there are. So di is 2, 7. All right. And then one other kind, acid. So how about this one? What's the first thing you look for in an acid? A leading proton, hydrogen. That indicates an acid. Then you look at what follows it. In this case, NO3 is a polyatomic ion. So you look for the name of NO3. Now this is +1. Protons, they're always +1. That makes this one -1. Of course, that's the way it should be. And you look in your, we're out of time. And then you look in your polyatomics and you find this is nitrate. Right? Now, why don't we say hydro to begin with?
It's polyatomic.
Because there's an oxygen. There's an oxygen in there. You don't say hydro to begin with. You just take the polyatomic, or whatever this happens to be, and if it's an 8, you change it to ic. It's nitric acid. Okay? What if we say hydrosulfuric acid? Hydro means there's no oxygen in there, right? So it's not this one. That's oxygen. It would be this one. And then hydrogen, which is 2, and it has to be aqueous. So H2S is hydrosulfuric acid. Now it says sulfuric acid. There's an oxygen in there. And ics are derived from aches. So the ic derives from sulfate, SO4 2 minus. Then you have to balance it with protons, like hydrogens. But it takes 2 of them because each one of these is +1. So that's sulfuric acid.
A single proton is a hydrogen.
Yes. It's a hydrogen without an electron.
So when they're saying proton bombs, they mean hydrogen bombs.
Yeah.
In like Star Trek and stuff, fire the proton torpedoes. It's
Oh, I thought it was photon torpedo.
proton. I thought.
It's still fictional, right?
I mean,
Okay, we're out of time. We'll see you on Wednesday.
Okay, see you Wednesday.
We also have a lab on Wednesday.
Okay.
yeah.